So welcome everybody to our today's seminar, a joint seminar between TFDC Committee of the TRB and NGTS seminars of the University of Michigan. Today we are pleased and honored to have Dr. Vikash Gayah with us. Dr. Gayah is an associate professor in the Department of Civil Engineering, Civil and Environmental Engineering at the Pennsylvania State University, Penn State. He'll present today his latest research findings on application of deep reinforcement learning for perimeter metering control. Dr. Gayah received his PhD degree from the University of California, Berkeley in 2012. And his research focuses on urban mobility, traffic operations, traffic flow theory, traffic safety, and public transportation. He has editorial roles in several different well-known journals like Transportation Research Part C, Part B, Accident Analysis and Prevention, IEEE, Intelligent Transportation Systems Magazine, and Transportation Research Records. And he's also a member of the committees, the TRB committees on access management and traffic flow theory and characteristics. Has received several awards like Newell Award for Excellence in Transportation Science, New Faculty Award, multiple Transportation Research Board, Outstanding Paper Awards, and Faculty Early Career Development Award by the National Science Foundation. With all that said, thank you again, Vikash, for being with us today, and the floor is yours.
Awesome. Well, thank you for that very long but very kind introduction. Really appreciate the opportunity to do this. So are you guys seeing my screen?
Yes.
Okay, you're seeing the PowerPoint?
Yeah.
Awesome. Okay. Well, yeah. So thanks again for the invitation. I really appreciate the opportunity. So today I'm going to talk about application of deep reinforcement learning for perimeter metering control. Actually, we presented on this a little while ago, and so now we have some I think some more new and exciting things to talk about related to this. Again, I'm Vikash Gayah. I'm associate professor at Penn State. And before I go on with the actual presentation, I just have to acknowledge and thank collaborators on this work. The primary driver of this research, the one who's actually doing it, I'm just sort of helping, is my PhD student, Dongchin Zhou. He's a third-year PhD student who's been instrumental. I mean, this is his PhD dissertation, and then this work has been funded by a couple agencies, NSF and Penn State Institute for Computational and Data Sciences. So. With all of that long preamble, what is the point of this work? So I work on urban mobility, and particularly related to macroscopic fundamental diagrams. And so what macroscopic fundamental diagrams is a tool that helps us simplify the modeling of transportation networks, urban transportation networks. And it does that by allowing us to look at sort of vehicle behavior at a regional level, as opposed to sort of a link node or a more microscopic level. So the justification for this are, traffic networks are complex. I mean, they're very complex systems. So this is a picture of downtown San Francisco, just a small portion of the city, not even a big piece. And if I were to model the behavior of downtown San Francisco in a microscopic way, I'd have to break this up into its individual pieces. So this is what this would look like. And you can see now there are hundreds of individual links, hundreds of nodes that I would have to model. I'd have to know about their behaviors, their fundamental diagrams, free flow speeds. I need to know how the intersections operate. And then I'd have to simulate the behavior of each of these elements or individual vehicles on each of these elements. There could be hundreds of thousands of vehicles that I have to simulate, and that is very computationally complex. So a newer paradigm that has, emerged in the late 2000s is a regional level model. And so in a regional level approach, I just sort of draw a big circle around this network, and I say, I don't really care where vehicles are or the behavior of individual vehicles in this network. I just kind of want to know, is it congested? Is it not congested? How congested is it? How productive is this transportation network? Okay. Again, I don't care about the details. I'm just looking at the overall big picture. And this kind of method works really well if the network is kind of congestion is spatially homogeneous across that network. So meaning all areas of the network are more or less have the same level of congestion at any one time. Now that's often violated in networks, but that's not really even that big of a problem, because we can just break it up into a handful of smaller regions where we do maintain that spatial homogeneity of congestion across each of these regions. So we can just subdivide it into smaller networks and model the behavior of each. And what really allows us to use this approach is the existence of well-defined relationships between network productivity and accumulation within these regions. That's our macroscopic fundamental diagram. And so it's been shown to exist, this has been studied for quite some time, but only recently shown to exist, that these relationships between productivity, network productivity, for example, average flow, or the rate that trips are completed in a network, or VMT allowed, is nicely related to the level of use across this region. And the level of use can be the density, number of vehicles in the network, or something like that. So this is empirical data from different days, different demand patterns, different times of day, different days in the same city. And when aggregated, individual links are aggregated at a regional level, we get this nice, well-defined, reproducible relationship between average flow and density. Call that a macroscopic fundamental diagram. And what's nice about that is we can use this to then model the behavior of a network in this regional way. So we take the network, divide it up into regions, look at how vehicles are coming into one region, leaving another region, moving from one region to another. Again, we don't know exactly where the vehicles are within the region. We don't know anything about specifically what's going on with that inside at individual locations within the region. But this, if we only care about sort of the big picture behavior, this can be good enough to model the urban traffic network dynamics. So this MFD-based modeling framework has been used actually in the literature in the past 15 years or so to develop a whole host of different types of urban traffic control strategies. So one is congestion pricing. How much money do we charge vehicles to enter sort of a protected area in a network? A lot of cities have implemented congestion charging, but it tends to be either static, so a static fee to enter the downtown, or even if it's a dynamic fee, if it changes with time, it really just changes with time and historical patterns, and not really with what's happening inside the network. This MFD-based approach can allow us to charge the appropriate fee based on like how many vehicles are actually in the network, and particularly how much congestion a single vehicle is contributing to within that network. So a little bit more dynamic congestion pricing. It's been used to answer questions about space allocation. So we have a bunch of streets in a network. What fraction of streets do we want to dedicate to specific modes? Knowing, if I take, space away from cars, the cars are less productive, but then I dedicate some space to transit, maybe the transit becomes more productive. And so there's a trade-off there. And we can use this macroscopic approach to get an answer like, it's optimal to dedicate 20% of the streets to buses, for example, or 20% of the lanes to buses. Now, this doesn't tell us where to put those bus lanes, but it gives us a good idea of what we should be aiming for. And then we can then figure out exactly where to distribute that. Actually, in my personal research, I've used this macroscopic approach to study street network design. So what happens if we have different street network configurations, one-way streets, two-way streets? It has different sort of impacts. We have higher flows with simpler intersections, but then maybe vehicles have to reroute. And so we use these macroscopic relationships to sort of combine all these competing features to really study the street network design. But the biggest, and vehicle routing is the last one. So at a regional level, if I'm a vehicle, I'm going from region 1 to region 5, like what's the path that I want to take? Again, not the specific links that I want to take, but in general, do I want to go through the top of the network, the middle, the bottom? This is a regional level routing question. But the most common or notable of these strategies that are sort of unlocked by the MFD-based approach is perimeter metering control. And what perimeter metering control is we have a network. Vehicles are entering this network. We want to protect this network and keep it from becoming congested. And so we will then limit the number of vehicles that can cross that perimeter to enter that protected region. And we do that in a way to keep that region operating at its peak productivity at any point in time. So we call that, it's called gating or perimeter metering control. And so this can be done, implemented with a lot of different ways. You can implement it with just traffic signals. It can tell us how to time the traffic signals along that perimeter. You can use pricing, kind of related to the congestion pricing. But the idea is keep the network from getting congested so that it's operating at its peak efficiency for as long as possible. And keep the congestion, move that to areas where it might not be as damaging, a long bridge or a freeway, for example, where, yes, it could be damaging, but there's more space to store vehicles. If we store those vehicles within the network, they end up degrading the performance for everyone else. So this has been studied again for like the last 15 years, and there's a lot of different approaches to perimeter metering control that have been proposed. But most of them require a really detailed knowledge of the MFD of the network and detailed models of the underlying traffic dynamics. So the most state-of-the-art is model predictive control, but we need to know in a model predictive control approach, it's really an optimization type approach, where we need to know, like, how are vehicles moving around from region 1 to region 2? How do they route themselves? We need to know what is the MFDs of region 1, region 2, all these different regions that might exist, and how do vehicles move from one to another? There's also feedback-based methods. These feedback methods require some sort of like a set point of congestion. So we have to set ahead of time, here's where we want to operate. So we kind of need to know what the MFD looks like to pick a point. We say, this is the point that we want to be at. And then the feedback-based methods, if we're too congested, it just restricts vehicles from entering. If we're not congested enough, we allow more vehicles to enter, really trying to maintain that point. Recently, there's been some model-free iterative learning approaches, but they require, again, that set point of congestion. We need to kind of decide ahead of time, where is it that we want to operate, which is really fine if you have one region. But if you have many regions, we don't know where we want each one to operate. They might be in conflict. Not only that, but this information is really hard to obtain. The underlying equations of traffic dynamics are fine, like if I'm just doing a pencil and paper example, but for real networks, it's really hard to kind of find that information out. There have been studies that have actually estimated the MFD, and actually more of them in recent years, to estimate the MFD using different empirical data sources. But even still, we don't know the MFD for a lot of cities. We just don't know what it looks like. Not all cities are instrumented in such a way that we have this information. Those that do estimate a network's MFD, they tend to provide the relationship between average flow and average density. But actually what unlocks this MFD-based approach is we need what's called an output MFD. We need to know the rate that trips are completed or the rate that vehicles are leaving a region as a function of the density. And empirically, we actually don't have a lot of those. And not only that, but we're doing some research now that suggests that even though these two, the flow MFD and the output MFD, are related, they have some sort of inconsistent behaviors, which means we can't just take the flow MFD and assume it looks like the output MFD. Actually, it can look completely different. And then these MFDs are sometimes really funny looking, to put it simply. They are subject to errors due to measurement errors. There's large amounts of scatter or hysteresis or other phenomenon where, it's not just where we have one density and we get one flow. We might have many flows that are observed, and we don't really know how to integrate that into some of these existing approaches. So with all of that as a preamble, the purpose of our work is to apply model-free methods, specifically deep reinforcement learning, to the perimeter metering control problem. So we have two kind of separate goals here. The first is develop a perimeter metering control method that doesn't require knowledge of a network's MFD or any of the underlying traffic dynamics, that is stable, so it's able to converge consistently and across different scenarios. That's effective, meaning that it's able to compete with sort of a state-of-the-art MPC method that has all of the information, but our method doesn't have that information, but it's still able to sort of provide similar results. And that it's transferable. So one of the issues with any sort of reinforcement learning or deep reinforcement learning method is you train it in one situation, you apply it to another situation, it doesn't perform well. And we want to actually directly address that, make sure that our methods are transferable. And then once we have that done, we actually then want to improve upon it. So we want to have enhance this method so that it has improved learning performances and is scalable to network problems at a really large scale. And so the second goal I'll talk about towards the latter piece of the presentation. But you'll see what I mean when I say we want to make sure that the methods that we develop are actually able to be applied in realistic situations. So it's not just a toy, we're going to develop it for toy examples, but demonstrate that we can actually implement this in reality. So with that, before we get into sort of what we did, a little bit of discussion on reinforcement learning in general. So reinforcement learning and deep reinforcement learning is just essentially a more complex version of reinforcement learning. In reinforcement learning, we have an agent that makes decisions and then learns about the consequences of these decisions to inform future decisions. Okay, so you know, it's like any of us. Like I wake up, I make a decision for the day. There's a consequence to that, and that helps me to make better decisions tomorrow. So we have our agent, we have an environment. The agent is kind of operating in the environment, and so from the environment, the agent sees a little bit of information. We call that a state. Okay. So the state tells the agent sort of more or less what is happening in the environment right now that's relevant to the agent. Based on that state, the agent takes an action, and that action influences the environment. So the agent makes an action, tells it to do something, or it makes a change or sets a parameter, and that impacts how the environment evolves in the future. And then based on that, the agent receives some information. We call that a reward, based on what sort of the result of that agent's action. Okay. And so then the agent does it again, gets an updated state, makes an updated action, gets an updated reward. Okay. And so the goal of the agent is to select the proper actions to maximize both the reward that it receives, like immediately, but it also wants to consider future rewards. Okay. So like, I don't know, I love to eat. And so at any point in time, I would say, like, I'm going to eat a snack, right? And that's great. It'll bring me immense reward right away. But in the long run, like that's going to be a problem, right? Like I can't eat all the time. It'll make me feel ill in the future, right? Like I'll be slow, I'll be lethargic, right? And so I also want to consider like the happiness that eating brings me, but also like, it might bring me some unhappiness in the future. So the agent considers both the immediate rewards and future rewards, although the future rewards are discounted essentially because they matter a little bit less than what's happening in the near future. And so the agent learns by trial and error. At the very beginning, the agent has no idea what to do, right? So it's just like, okay, like I'm going to try something. I'm going to pick an action, and then I'll learn from it. I'll pick another action, and it does this kind of randomly, right? So the agent doesn't know anything, so it has to essentially, base its decisions essentially randomly. But then as it learns a little bit more about the rewards or the result of these actions, it can start making more and more informed decisions. So at the beginning, it flips a coin, right? But after several days, the agent will say, well, I know if it comes up heads, I know if the state is in this way, when I make this action, that's bad. So I should do the opposite. I can make a better action. And I'll show you an example of this specifically in the perimeter metering scenario case. So let's imagine that I have some network here. So this is this dark circle, or the solid circle is my region. I have vehicles entering this region, so that's my arrows there. And then I have this dotted line, that is any sort of perimeter metering control that I'm going to implement. And there's an underlying macroscopic fundamental diagram in the background that sort of relates my productivity of my network on the y-axis with the use of the network on my x-axis. You can see the productivity goes up as density increases, and then it goes back down as it gets congested. But the agent doesn't see that at all, okay? And one day, I have a congested scenario. So the actual density within this network is N1. That's my current state. And again, the agent just sees this current state, flips a coin, makes an action. And so in this early day, the agent says, you know what, I'm going to really restrict, I'm going to really open up this network. I'm going to let a lot of people in, okay? If the agent lets a lot of people in, what will happen is more people start entering, the network's going to get more congested. So if I have less restriction, the network gets more congested, and all of a sudden it's operating in a more congested state. This is not good. Okay, so the agent will get a reward or some feedback that says, ooh, that was a really bad choice. So the next day, if this state happens again, the agent says, you know what? I did less restriction. I'm going to try more restriction now. I get more restriction. I'm gating more tightly, letting fewer vehicles in. Well, then maybe the congestion reduces a little bit. I get a little bit higher efficiency in my network, and the agent says, oh, cool. That was a good action. That's great, So that would be in a congested scenario. And in a single region, this is pretty obvious. And that's why we can step through this and look at it. And as another example, if it's initially uncongested, right? So I have a free flow state here. the agent flips a coin, maybe it says, okay, I'm going to try more restriction, right? But if it's uncongested, there's no reason to restrict more. We want more vehicles to enter. By restricting, I'm actually going to reduce the efficiency of the network, right? I'm going to have lower flows. The agent says, sees that this is not a good thing. So the next time he opens it up, has less restriction, we allow more vehicles into the network. Maybe it doesn't become too congested, but it increases the overall efficiency. Everyone's happier. And over time, the agent will learn that, what I really want to do, it doesn't matter if I'm congested or not congested. What I want to do is I really want to get the network to this final state where my reward is the highest. Okay? Again, we can see this with a simple single region example, because it's, we know the answer to this. It's been proven many times in different contexts. We know the answer is to operate at this highest efficiency level. What's not so obvious is when I have multiple regions where congestion in one region, by reducing that, I can create congestion in another region. Now I have a trade-off where it's not really obvious what I want to do, okay? So we start off with a 2-region network where the traffic dynamics are governed by well-defined MFDs. So we know there's initial accumulations, there's some demands of vehicles entering each region. Some of the demand enters a region and stays in that region. Some of the demand enters a region and moves to the other region. In this case, R2 is like our downtown, R1 is like our suburb, and we're looking at sort of like a morning commute scenario. The equations there are these are the equations of the traffic dynamics. In a 2-region network, they're actually not that complicated, but when you get to more and more regions, it can become quite complicated, but we wanted to start something really simple. Now, all I'll say is this is the scenario we're starting with, but in all of the work that we're doing, the dynamic equations and the MFD, even though it's known in the numerical simulations, that represents our environment, they're unknown to the agents that we're training. They don't see any of this, okay? They're only gonna see the limited piece of information that we tell them. So this is, again, the scenario that we're considering. We're looking at a morning commute where there is a large outer region and vehicles trying to generally move to a smaller inner region, again, representing the morning commute. And the smaller region is a little bit, has a lower fundamental diagram because it's like the city center essentially. And so we do some experiments to simulate the morning peaks with more vehicles traveling to this congested city center than staying in the uncongested periphery. And so the only thing I really want to show here on the right-hand side is how the accumulations would naturally evolve over time. So region 2, in the scenario that we're considering, region 2 just gets more and more congested over time. So the accumulation's increasing. Whereas region 1, the suburbs, the accumulation goes down. So we have a lot of congestion in the center, no congestion in the periphery, or not no congestion, but less congestion in the periphery. Now, we're not dealing with a perfect world here. So in our simulations, what we do is, yes, there's a relatively stable demand pattern across different days, again, representing this morning commute. But on any given day, we can have errors both in the demand or errors in the MFD. So the solid lines here kind of represent the average demand pattern, but on any given day at any given time, the actual demands you can see vary considerably. So we have these, this sort of like randomness here representing, okay, some days or sometimes there's higher demand than expected, some there's lower demand than expected. And these errors are completely random and change from day to day, change from time to time, randomly generated. In addition, the MFDs themselves, I think I mentioned, the MFDs have scatter to them, right? So we also estimated, we also assumed that there was some level of randomness in the level of productivity of the individual regions based on their accumulation. So it's not like a nice smooth MFD line, there's randomness associated with this as well. And we developed different types of agents to implement in this scenario. So the first type of agent that we're going to consider mimics the bang-bang control policy. And so essentially what the bang-bang policy is in the single region scenario, if it's congested, you just kind of close up shop. Meter as restrictively as possible. But if it's not congested, you open up the doors and let people in at the maximum rate that they can, okay? So that's the bang-bang. It just goes, there's no in between. It's just like the most restrictive or the least restrictive. So in the we call it the BRL for sort of bang-bang reinforcement learning. We just restrict the actions of the agent, and the actions here are these control variables that limit how much of the flow is able to move between the two regions, we allow them to either be the minimum value or the maximum value, nothing in between. Okay. The agent itself only sees an estimate of the state, and that is the accumulations within the region and an estimate of the demand. So how much the demand is at that given time. Our second agent, we call it the DRL, or discrete reinforcement learning. We said, well, you know, if this bang bang, it's like either the min or the max, like there's no in between. So we said, okay, well, what if we use discrete actions where we allow the actions to sort of be within a range of this minimum maximum, but we just did a discrete range. So we discretize the potential actions that we can take. And we also, just to reduce the complexity, we just, for a given action, we only allow the next, for a given level of metering control, we let the action be either stay at that control, move up a level, or move down a level. Okay, so this is like, it just, in this case, it doesn't like change rapidly. It can only change slowly over time. So it can slowly increase, slowly decrease, or kind of stay the same. But we can't just go wild. And that's only because if we allow it to sort of move around in a discrete space, the action space becomes way too big, and our agents are not able to learn effectively. And then the last one is a continuous action space where we just sort of open it up. So we have an agent that allows for continuous actions, not discrete actions. And we say, you can take any action you want, like anything in the range from the minimum to the maximum, anything's on the table. So I think we would expect, if I was in a classroom or something, I might pull the class, but I don't know, how we can do that in the Zoom effectively. But I would think that, like, as the actions get more options, we would have better performance. So the bang bang, there's only 2 options, like that maybe is not the best. In the discrete version, we have like all the options. So maybe that is a little bit better. Sorry, not all the options, more options in the bang bang. So maybe it's a little bit more effective. And then in the continuous space, like it's even more effective because everything's on the table. That would just be my hunch. I hope it would be your hunch too. So we'll see if that actually comes into play. And so then we tested the performance of our deep reinforcement learning agents compared to no control, meaning, there's no metering at all. Everything, the gates are open and everyone is able to come and go as they please, which is basically saying that we set the control parameters to the maximum value. We also test this compared to the model predictive control, which is the state of the art. It's an optimization-based method. It knows what the MFD is. It looks at the current action. It looks at the future actions. It tries to balance between these. It knows how vehicles move from one to another. It basically has all of the information. So it has information on what's going on right now. It kind of knows what's happening in the future, and it can update based on this. So I would say it's the all-knowing model predictive control. And then we compare it with our 3 deep reinforcement learning agents, our bang bang reinforcement learning, our discrete reinforcement learning, and our continuous reinforcement learning. And the different types of reinforcement learning architectures are listed here. That's not my area of expertise. So I can answer some questions about it, but I just want, for anyone who's interested, you can kind of see what types of RL methods we're applying. Okay. So now we'll just go to the results. And so I'll show a picture and then explain the picture, and then we'll discuss the results. So first, I'm going to talk about the results when there's no uncertainty. So I mentioned before, the demands, the actual demands can differ from the average demands in a random way, and the MFDs can have some errors. So we actually tested these first when these errors did not exist. Okay, so just consider this like a completely deterministic environment. We have 4 or 5 different lines here. Okay, the gray line is the performance of the network in the no control case. The performance is measured by the cumulative trips completed. So basically how many trips are completed at the end of our morning commute scenario. And the higher number of trips completed, the better, the more efficient, the more vehicles we're able to serve. So the gray line here is no control. And of course, this is shown as a function of the number of training iterations. So no control, no control in MPC has no training. So they're going to just be a flat line here. You can see under no control, we have some number of cumulative trips completed. The red line is the model predictive control. You can see in the model predictive control case, it's higher than the no control. So actually doing some sort of metering helps. And then more interestingly, we have 3 lines, our BRL, our DRL, and our CRL. Our bang bang control starts off, you can see here, the performance is really bad, actually extremely bad. It's worse than no control, which is not good, okay? The dark lines represent sort of the median of many agents that we trained. The colored areas associated with those lines are the range of the agents that we trained. And really we wanted to do this to demonstrate that, each time you train an agent, it's a random process. So maybe you can get really lucky and it's good. Maybe you can get really unlucky and it's bad. So we wanted to show kind of like the median and the range, okay? And you can see with the blue line, our bang bang controller, well, goodness, it's the median is terrible, the best is terrible, the worst is, it's just terrible all around, okay? As it's able to learn, as we increase the number of training iterations, you can think of training iterations as like, we learn from the decisions of day 1 and we apply them to day 2. That would be a training iteration, so day to day. We can see that its performance generally gets better, kind of flattens, and after 250 iterations, it seems like it's plateauing, although if we ran it for many times, maybe it will do okay. I would venture to guess that it would eventually learn, but not within the space of 250 days, which is a year, if we were to apply this, from in reality. So we don't, it's not good. The orange line is our discrete agent, and you can see that the discrete agent, again, it also starts lower than the no control case. And actually, its performance is really flat over the course of like the first 75 days. But then after a while, it starts to figure it out. It starts to figure out what's happening, what are the results of my actions? How do I change these actions to maximize my result? And then after about day 75, it starts to really learn. And it learns at a pretty rapid rate, and it's pretty tight. Like the range of performances, like it's always learning, that it's not as wide as the bang bang controller. And then eventually its performance kind of plateaus. Again, if we ran this forever, I'm sure it would improve and improve and improve, but it's generally stagnant after a year. Its performance is fine, but it's not as good as the MPC. The green one is our continuous agent. The continuous agent actually starts off kind of lower than the discrete one, but it starts learning immediately. It learns like rapidly what to do. Its performance gets better and better. And then eventually the performance is about the same, if not even better than the MPC, which is quite remarkable actually. Maybe it's remarkable because it's overfitting, it's a discrete environment, so a deterministic environment, sorry. So it's just kind of like, maybe it's cheating a little bit because we're just testing it on the same problem over and over again, and eventually it'll just kind of figure out the best thing to do. So we also tested this in an environment with a lot of randomness. So we have randomness in the demand, we have randomness in the MFDs, and the same general patterns hold, right? The bang bang is not that great. It eventually kind of learns, but not in a good way. The discrete agent, the orange one, it starts off really stagnant, but then starts to learn and approaches sort of gets close to the MPC, but not there. And our continuous agent really does a good job. Like it starts off really poor. It's worse than if we did nothing, but then it learns quickly. And actually its performance is comparable with, if not better, to the MPC. So that's kind of nice. It's kind of a proof of our concept. So we're happy about that. We're able to apply this deep reinforcement learning to a perimeter meter control problem. We look at sort of what's happening within each network. So this is the accumulations in each region over time. The key here, I've kind of highlighted the critical accumulation or the accumulation associated with the max productivity. And in both, if you look at our agents, the MPC and our agents, they're essentially trying to keep the accumulation in each region as close as it can to that maximum accumulation. Sorry, it's not the maximum accumulation, I apologize. The accumulation that maximizes the performance of that agent. So that's kind of what I'm showing here. You can see here the MPC, the red line is really trying to keep region 2 at its highest productivity. And our agents kind of try to do that. The BRL is a little late to the game, but the DRL and the CRL kind of really, we're not exactly there, but they're kind of hovering there, which is really nice. I'm gonna skip this for time. If you compare the performance, again, the cumulative trip completion applied on a different scenario. Again, no control is really bad. It has the lowest values. All of the other control cases have higher values. And then we want to really compare the MPC to the discrete agent. You can see that the discrete agent is a little bit worse than the MPC, a couple of % worse, but it's in the ball game, right? Like and again, it doesn't know anything. It doesn't know as much information as the MPC, but it knows something, but just it doesn't have the models of the traffic dynamics. It doesn't know what the MFD is. And the continuous agent actually has a little bit of improvement to the MPC, which is really nice. This is all well and good. It works on a scenario. So what we also did was we tried it. We tried these agents, tested them on scenarios where we know the answer. So in an uncongested scenario, so we just change the demands so that everything is going to be uncongested. If we know that the network is always going to be uncongested, we know what the answer should be. We should never do any sort of metering. The control values should always stay at that highest level, which is 0.9. And when we applied it to that case, that's exactly what we found. Our agent was able to learn pretty quickly that we just want to keep our control value at 0.9 and essentially do nothing. So in uncongested cases, our agent is able to learn, we do nothing. And then we also tried a scenario where the city center, region 2, is extremely congested. In this case, what you'd want to do is have as restrictive metering as possible. We know this, the MPC tells us this. We know it first from our knowledge of traffic dynamics. And again, our agent is able to learn that that's what we want to do. Limit that vehicle movement from region 1 to region 2 as much as possible and actually maximize the movement of vehicles out of region 2, which is exactly what it does. So that's very promising. It kind of behaves like we expect on scenarios that we know, and it actually provides answers that that are reasonable in scenarios that we don't know the answer to. So that's good. We also, again, we talked about transferability. So we also tested the performance of the agents on scenarios that it has never been trained on. So maybe the starting accumulation is a little different, or the demands are scaled up or down by some amount, or the MFDs are bigger or smaller than the situation that it was trained on. These pictures are not terribly exciting, but all I wanted to kind of mention here is the lower the orange and the blue curves, the better that our agent performs. The orange curve, the lower the blue curve is, the better our agent performs. The orange curve is the MPC. And essentially, we're looking at different levels of variation. So this is with similar or higher initial accumulations. And you can see that we're always still doing better than the no control case, even though now we're applying this agent to a scenario that it really has never observed before. So in this case, the scenario has different starting accumulations. In this picture, it has different traffic demands, higher or lower traffic demands. And in this picture, we have different MFD modeling errors. So basically, the MFDs are functionally different than the scenario that we sort of tested or sort of trained our agents on. You can see here, if the variation in the MFD is quite large, actually then our performance starts to get really, it actually becomes worse than the no control case. So with the MFD variation, you kind of have to be, you can't just, you can't take an MFD for like a big city like Manhattan and then train an agent there and then apply it in a small place like State College. It's a huge difference. We have big problems. Okay, but I know I'm rushing through this part, but I wanted to get to a more interesting piece. And to me, the more interesting piece as well, we have achieved our goal. We have an agent, it's stable, it's effective, it's transferable. But even though these results are promising, imagine that you gave me the keys to a city, or someone gave me the keys to a city and said, yes, go ahead and implement this, okay? And these are the same training curves that I showed before. The one real big problem is this agent needs to learn over time. And if someone, if a traffic engineer, a city traffic engineer gave me the keys to their city, on day one, my agents are all performing worse than if I had no control. So imagine like this, New York City says, Vikash, let's implement deep reinforcement learning for perimeter metering control. You go ahead and you do what you need to do. And on day one, my performance is worse than before they gave me the keys to the city. They would start to doubt me. Day two, it's still worse. Okay. Sometime by day 3, they're taking those keys away from me. They're saying, yeah, you know what? You said it's going to work, but it's not working. We don't trust you anymore. Okay. And that's because the agent needs time to learn, one, But not just that, is that the agent, for a lack of a better term, the agent's not smart at the beginning. The agent on day one is making completely random actions, okay? And you can imagine just pure randomness in its actions are going to make situations bad. It's not going to be, you know, in our case, actually, it's so bad that it's worse than if we had absolutely no control. So what we did then is we said, well, what happens if we take a little bit of knowledge of how traffic networks evolve and give our agents what we call a warm start? We call it domain knowledge, okay? Or yeah, so we take our domain knowledge of traffic networks and we said, listen, on day one, I know you want to start randomly, but you really shouldn't start randomly. You should look in this direction. So we're not necessarily saying exactly what to do. We're just saying instead of randomly picking, you know, pick on this side of the ball, don't pick on that side, okay? So we call that our domain knowledge, and we use it to guide the agent's exploration. So here's an example. In our continuous agent, what we did was we said, look, if region I is really uncongested, so region I has a accumulation that is much lower than the critical accumulation, and region J has an accumulation that's much lower than the critical accumulation. In that case, you really shouldn't do any metering at all. We know that, like we're sure of it, okay? So in that case, let's just go ahead and, you know, we can do different forms of this, but in this case, we said, in that case, if there's no congestion whatsoever, agent, you don't even need to do anything. I got your back. I'm going to tell you what to do. Set it to the maximum value, okay? If everything is really, so the green values here are situations where we're telling the agent sort of, this is kind of where you need to operate. So the arrow is like, we're going to set that value. And I see a couple typos here, so I apologize. The arrows should really only point to 0.9, which is the maximum value. The squiggly line is, we're going to sort of say, start with an average of this value. So in that case, it's, you know, go ahead and be completely random, okay? And so when for any region that's really uncongested, we just say, you don't need to meter that region. It's really uncongested, just let it be. That will take fewer decisions away from the agent, and it also keep it from making bad decisions while it explores and learns. The red cases we're saying, like, you know what, agent, we have no idea. We don't know what's going on. You go ahead and figure it out. Make your random guesses. Do whatever you need to do. We have no idea. We hope that you can figure it out. And the yellow is kind of like a hybrid. We're giving you a little bit of information, but you can also search around that information. So we can implement that for, we tried that for the continuous agent, and we actually tried it for the bang bang agent as well, because the bang bang agent just has very few actions. It's, you know, it's either minimum or maximum. So we're telling it, hey, in some cases, just always pick the maximum. In some cases, try both. And in some cases, try anything, but maybe tend towards the maximum because we think that's where the best gains lie. And what's interesting is if I take that picture, and this is the case where there's a lot of variation in the environment, the blue line where, you know, where there's no prior knowledge or prior, you know, domain knowledge, which is really starts off really bad, we move all the way up to the orange line, which you can't really see because it's just at the top. It starts off really good and it keeps learning. And it's bouncing up, you know, really good. Same thing with the green. The green actually ended up being really, really well, the continuous agent. But again, it started on day one really poor. Just adding this domain knowledge shoots it up all the way to the top and it stays there, okay? So that's really nice. Like if New York City handed me the keys and I give them that orange or that red line, they'll say, well, this is way better than when we did nothing. Okay, you can keep trying this. And yeah, maybe the performance will fluctuate and get a little worse on one day or not, but it's never gonna get horrible. And this agent is only gonna improve its performance over time. What's also nice is when we start applying this domain knowledge, this problem is kind of fairly simple for 2 regions, but in 3 regions, there's a lot more actions that can be taken, right? The scale of the problem kind of explodes with the more regions that we have. It increases more than exponentially with the number of regions that we have. And so we said, okay, well, let's try this with a case where there's many regions, 3 regions instead of 2. And what we found is kind of the same thing. When we looked at the 3-region case, without the domain knowledge, the bang bang agent, you know, it's kind of living here at the bottom. Like things are horrible. It's worse than the no control, and it's really never learning. But when we apply the domain knowledge, we move up to this orange line where it starts off really nice and it keeps improving over time. Same thing with the green, our continuous agent. Our continuous agent does okay eventually in the 3-region case. It starts off pretty bad, it learns quickly, and then it eventually kind of bounces around here, but its performance never rivals the MPC performance. When you add that domain knowledge, you get the red line, it just starts off, kind of really well, and then it just improves and improves and improves. So that achieves our second goal, which is how do we make this implementable? How do we make it so that we provide a little bit of knowledge about what we know about traffic dynamics to help an agent that's normally kind of, for lack of better terms, not really smart at the beginning. And we say, look, search in this direction. These are the most promising ideas, or this is the most promising thoughts that we have based on what we know as people about how traffic networks evolve. So with that, that's my presentation. In summary, we were able to develop a model-free deep reinforcement learning agent that works well to solve perimeter metering control problems with 2-region networks. We developed methods using both discrete and continuous action spaces. The methods are stable, so they converge well under uncertainty and measurement errors. Basically, the stability means it doesn't matter like where we start, it's always converging. The agents are always able to learn. It's not luck. We run these agents many, many times and they're always converging. That's why we showed the range and it always sort of improves. They're effective, so they're actually comparable with the state-of-the-art MPC, and the MPC has full knowledge of system dynamics, whereas our agent really just sees a snapshot every now and then of what's happening, and it doesn't know the underlying equations that are guiding this behavior. And they're transferable. We can train them on one scenario, we can apply them to another scenario that's fundamentally different than the scenario that we trained them on, and it still kind of works well. And then in implementation, one, we can use surrogates in practice. So I didn't actually talk specifically about the inputs or the states or anything like that. But there are surrogates for all of these that would exist in practice that we can actually use, like things that are actually measurable that I think can be measured in real time to apply. And then we can apply, improve the performance so that if we add a little bit of domain knowledge, we can improve its performance so it's actually implementable and palatable to like a city traffic engineer. So with that, I would like to say thanks. And if there's any questions, I'd be happy to take them now.
Thank you so much, Vikash, for your interesting presentation. So the floor is open for the questions right now. If anyone has any questions, please feel free to unmute yourself, raise your hand, or type your questions down in the chat section.
Hi, Professor Vikash. Thank you for your wonderful presentation. I see that your work is based on like macroscopic level of traffic simulation because it controls the percentage of the flow between regions. So I wonder if there are any reinforcement learning based application based on microscopic level, which is controlling the intersection on the perimeter to realize the perimeter control.
Yeah, I think that's a great question. So, there's been a lot of work on deep reinforcement learning for like individual signal control. I've done some of it with colleagues here at Penn State, and I've seen a ton of it, particularly in the computer science world, but also in the transportation world. So there has been efforts like that at individual signals. Within the context of perimeter metering control, there hasn't been, what I would say is there hasn't been work that has been done to sort of figure out the level of perimeter metering control that should be applied at individual intersections, that should be applied regionally. I think this is one of the first that looked at the level of perimeter metering control to be applied regionally. I do know that there's been some previous work that was published, I think by Mike Cassidy and some of his students that looked at, if I know what the level of metering control should be, how do I distribute that to individual intersections within a region? And that was done using deep reinforcement learning. So again, they used another model similar to like an MPC type model, I believe. Now this is not my work, so I don't know it with a great amount of detail, but I think they use another model to figure out like how much metering should be done. And then given that, they use deep reinforcement learning for the distribution of that amount at a microscopic level. I think it's very relevant, very related, but it's just a fundamentally different question.
Okay, I see. Thank you, Professor.
Thank you for the questions. Let's see if there are any other questions.
Vikash,
Hey, Yafeng, how are you doing?
hey, thanks
Long
for
time no see.
coming to speak our seminar.
Yeah, thanks for having me.
Yeah, interesting talk. I have a couple of questions.
Sure.
Can you share the slide, like page slide 25?
Sure thing. Yep.
So I'm just curious, your MPC is sort of benchmark, and then you sort of knowing, I believe, for the control horizon, and then you have a prediction. So you assuming you know everything in the future, is that right?
So in the MPC world, you're assuming you know most of everything in the future. So you know what the expected conditions are in the future, but it like maybe in the future there's still randomness, at least in the second row here. There's still randomness that can exist. So like if for some reason the actual demands are higher than expected, the MPC can then perform like less well. I think that's been shown. I think as the level of randomness increases, the MPC performance can generally decreases.
Yeah, that's a part I don't quite understand. I understand when you have uncertainty, then the deep learning, particularly for the continuous version, you sort of outperform MPC, right?
Yes.
Then
Yes.
for the deterministic case, why the MPC will give you the optimum value, even so theoretically, how it's possible that the deep learning can outperform MPC?
Yeah, I think so. That's a great question. My answer to that question in this case is now this MPC answer is a very hard mathematical program. What I suspect is happening is that we're not getting the global optimum.
Mm-hmm.
And it's because it's such a complex nonlinear mathematical program that we're getting an answer. It's not a guaranteed global optimal. That's what I suspect is happening. Because if you look at the parameters we're using a control horizon, a prediction horizon of 20 time steps and a control horizon of 20 time steps. So the MPC is not only trying to make decisions right now, but it's also pre-planning decisions for the next 20 time steps. If you think about that in a mathematical program, like it is just so many decision variables that I just don't think we're finding the global optimum. So I agree with you. And that's why like the difference, particularly in the discrete case, like I don't harp on the fact that the MPC, the reinforcement learning is doing better. Because I think it's basically the same.
Yeah.
But as we get more and more uncertainty, we do more and more better. And I think that kind of makes sense to me.
Yeah. I think it is. I think it's you have to be more cautious with making the conclusion here, right?
Yeah. And so I think I hope I did this during the presentation. I say like, it looks like it's even a better. To me, it's comparable to the MPC, and that's enough. Like that's
Correct,
where I am.
Correct.
I don't, it's a little bit better, but that's not an important fact because like that's a minor thing in my opinion.
A little bit better is simply because MPC is now solved for global optimality, right? It's the implementation issue. It's not
Correct.
It's not a methodology issue, right?
Correct.
Okay, thank you. Then for the domain knowledge one.
Yes.
I think in general, I agree. Incorporating that domain knowledge will help you to train the policy faster, right? But in practice, if you really want to implement something like, for example, traffic signal or this type of parameter control metering, you don't start from scratch, right? So you don't say, hey, New York City does not give you a chance to, hey, I start training the policy from the scratch. So therefore, you train the model using for example, in a simulated environment.
Yep.
And then you implement it, right?
Yep. Yeah.
So I think it's the problem over there is how can you ensure a policy you train in the environment that can be implemented in the actual environment, and how you accelerate that, right? So I guess my point is, in that situation, how can you incorporate domain knowledge? Because in the simulation already trained, well trained. And then you implement this policy to the actual world, and there's a discrepancy between the actual situation, actual world, and then simulation, right? But then you cannot simply find a domain knowledge to close the gap. Are you with me? So
Yeah,
my point is, if you start from scratch, incorporating that simple domain knowledge can definitely accelerate the learning rate. I agree. But the problem is less relevant if you really want to implement in practice. So what I'm saying is there's potential. Right, go ahead.
Oh, I think there's a couple of great things that you're keying in on there. So there's two parts of this implementation process, right? One is I just put it into reality and let it learn, and providing that domain knowledge. What we've shown is that it lets it learn faster. It also avoids negative outcomes, which is great. Mm-hmm. The second part is, I think we talked about those transferability tests, right? Like what I meant by that, and I did kind of rush over that because I thought I was going over time, is, the transferability tests were really like, I trained this in a simulated environment, but then I went and applied it in downtown New York City, and the reality is a little different from my simulation because we would expect it to be a little bit different. But the transferability, we show that it's still transferable. It's still giving us some positive outcomes, even though it was trained in a different environment. Now, we didn't make them very different, like a microsimulator versus reality. We mimicked that with different levels of uncertainty and things like that. I actually think that there's, and I think you kind of astutely have picked these 2 points out, because this is what we're doing, I think, next. We're going to try to combine this transferability with some domain knowledge and put them together, right?
Yes,
it's just that you're much smarter than I am, and it took me 30 seconds to figure this out, where it's taken us a couple of years to figure out this is where to go. So,
okay, so that leads to my second question. So I wonder, because I've been thinking, because if you think about in reality, and then so some policy has been implemented, right? So if you have, for example, traffic signal, for example, in this case, you can use your domain knowledge to develop a okay performance, a okay controller, right? So to ensure at least when you implement this policy in practice, then the performance was decent enough, and such that the DOT allow you to implement it. And then with that, you can do all those policy, and this is the process you design it. And then you collect data, and then you can do off-policy learning to train you reinforce learning to do off-policy learning based on the data you collect from the field, and with the policy that you design. And then you doing off-policy training to train a reinforced learning policy, right? And then you can implement that. So that is something I think might be a viable approach to try.
Yeah, I think I definitely agree. I think what was nice in our case, at least what I thought was nice, was that even if you just had this limited knowledge, you can, I still think like you can apply, if we wanted to, just turn over the traffic controllers to the computer essentially. By applying this domain knowledge, we still get, I think, pretty good performance. It's probably not the way to go, right? I think some sort of hybrid offline learning, as you said, a policy that exists now. But one of the things that would have to happen with at least in a reinforcement learning context, is it must have some opportunity to explore. And the only way to really explore is to try, right? That's either in a simulation environment or in reality, I think, try, in order to see if you can improve upon the outcome.
Right. Yeah. Okay. Thank you.
Thank you. That was awesome.
Yeah. Thanks.
Thank you, Dr. Yin, for the discussion and your questions. So let's see whether you don't have any questions in the chat section. But if you have any other questions, please feel free to unmute yourself and ask your question. Okay, I think it looks like there are no more questions. Thank you again, Vikash, for being with us today. It was a wonderful presentation. Hope to see you soon again.
Yeah, well, thank you
Or-
so much. I wish I could be there in person. Hopefully in the future we can meet. And
Yeah.
I really appreciate the feedback, Yafeng. I mean, it's kind of spot on with what we're thinking, and just I'm amazed. I'm amazed that that's exactly where you went. So thank you so much for organizing, and thanks
Thank
for
you.
the invitation. I really appreciate the time.
Thank you.
Yep. Take care.
Take
Have a
care.
good one.
Yeah. Bye.